All right. Thanks everybody for joining us for the August edition of the Data on Kubernetes Community Town Hall. Today we have David Fox. He's going to be talking about running Spark Batch data workloads on Kubernetes. David's from Dish Networks. He's a staff software engineer. Before we get to into the talk, I'm just going to go over some community announcements for you all. So first, of course, I want to thank our gold sponsors, Google Cloud and Percona. Thank you for sponsoring the community. That allows us to do things like this, which is have great talks and presenters to present to the community. And then also just want to thank our silver sponsors and then our community collaborators as well. And then a couple of community spotlights. I just want to point out some things that are going on. So Nelson Crepalde, he's just released a book, Big Data on Kubernetes. We're going to have Nelson come talk in October to talk about the book, but you can scan the QR code. There's a post he put on LinkedIn about the book. And then also Xing Yang, who's the SIG storage co-chair, also was featured in a blog post in the Kubernetes at 10 series. So you should check that out. There have been a total of six articles by the same author, all about Kubernetes at 10, featuring members of the community talking about storage and Kubernetes and how it's evolved. So you can check that out if you scan the QR code there. Okay, again, just always letting you know, DoK Day will be at KubeCon North America in Salt Lake City on November 12th. The call for proposals is closed, but we'll be making notifications, well, the CNCF will, about the schedule and which talks made it in on Monday, August 26th. So if you put in your proposal, you'll be finding out in a couple short weeks. Just to let you know, all access passes are increasing from $8.99 to $10.79 after August 26th, and it does require an all access pass to go to the co-located events. I also just want to thank so far, we have event gold sponsor Percona for sponsoring the event. I appreciate it. We're definitely always looking for more sponsors, but we have want to thank them for sponsoring so far. You can scan the QR code there if you want to register and get more information about DoK Day and KubeCon. Let's see, we've got some upcoming events. So we have a pretty full calendar coming up, but in September we have a doc talk with Vitesse, with Deepti Siguredi. And then we also have two people from Intuit coming to talk to us about at our town hall in September, on September 19th, empowering developers with easy scalable stream processing on K8s on Kubernetes. And that's with Sri Yai and Maurice, Vigith Maurice. So you can go to the meetup page and register for those events. And just a little shout out, we reached over 3,000 meetup members, so that's pretty exciting milestone for us. So thanks for joining us on our meetup group. If you want to learn more about the community, scan the QR code on the left. It takes you to our community page. If you're interested in sponsoring the community, you can scan the QR code on the other side, on the right, and we'll take you to our sponsors page for more information. And then lastly, if you stay till the end of our talk, we do a little quiz. Hopefully you've paid attention, and then also paid during David's talk, because we'll have some questions from the intro and the David's talk, and the winner can get a DoK shirt. Yeah, so before I introduce David, if you have questions, you can put them in the chat, and most likely we'll get them answered at the end. And yeah, so just put them in the chat and we'll relay them to David. So I will stop sharing my screen. Yeah, so David, you take it away and let us know about running Spark batch load workloads on Kubernetes. Oh, you are on mute.
Can you hear me?
Yep.
Okay, great. So yeah, hi everyone. So welcome to today's presentation on running Spark batch data workloads on Kubernetes. I'm David Fox, work at Dish in a data team, and I focus a lot on building, deploying scalable data applications in Kubernetes. So yeah, as data volumes continue to grow, organizations are seeking more scalable ways to process the data. And Apache Spark is a powerful tool for batch data processing, while Kubernetes has revolutionized container orchestration. So in this talk, I'm going to go explore how these two technologies can come together to create a scalable, cost-effective solution for data processing. Let's see. Yeah, so here's just a brief outline of the talk. So first, we're going to go over why we should run Spark and Kubernetes and why it's becoming increasingly popular. Going to go over the architecture of the Spark operator and how it simplifies Spark deployments. And then we're going to go over how to batch schedule Spark applications using Unicorn. And then finally, we're going to go over one strategy for reducing costs while also being resilient to failure. So let's dig in. So I'm going to give two demos in this presentation. And for the demos, we're going to be processing a data set, just an example data set that contains 112 million rows of yellow taxi trips in New York City. And it contains various information about pickup, drop-off times, trip distances, etc. But basically, the Python script will just process the data and extract long trips for a particular vendor and write to output file in S3 for some context. So yeah, why Spark on Kubernetes? So for those of you who don't know what Spark is, it's a distributed data processing framework that can distribute and process huge amounts of data, gigabytes to terabytes or more, over many machines. And so Spark and Kubernetes, they marry well together because the distributed nature of Spark across many machines benefits from the parallel processing. And with Kubernetes running in the cloud, that has the burstable capacity of spinning up resources on demand and scaling back down when processing is finished, which ends up saving you costs. Another incentive for our team to use Kubernetes for running Spark workloads was the resilience to spot failure in auto-scaling groups. So there's a lot of data stored from various operations in memory and on disk, a lot of disk I/O. But when a spot instance is terminated, it's very difficult to kind of reattach and reuse kind of data that is stored on attached EBS volumes. But in Kubernetes, there are standardized and automated mechanisms to recover from node failure by reusing data from persistent volumes. So, and finally, you can there's reduced operational overhead because you can use the same underlying infrastructure to run many different Spark jobs. So yeah. So basically, Spark applications are submitted to the cluster and run and managed on Kubernetes through a Spark operator. And here I'm showing the architecture of the operator. And here's the sequence of events that happens. So first, the user will create a Spark application object using kubectl. And then through the Spark application, through the API server, the Spark application controller will get notified and sends a submission to the runner to create a driver pod here. And it's the driver pod which is orchestrating the Spark job. It contains the critical metadata, the execution status, everything. This is like the main driver of a Spark application. And then subsequently, the driver will request executor pods. And the executors are the guys doing the work. And then, throughout the Spark application's lifecycle, the Spark pod monitor will track the status of the Spark application and report the status back to the application, whether it's in progress or completed. Oh, sorry. So yeah, it basically this whole process automates the deployment of Spark applications and basically just streamlines the entire workflow from execution to monitoring. And so here's an example of Spark application manifest and its spec. And here you can specify everything to do with complete Spark application from the Spark version, the type. Here we're using Python, but you can use Scala and you can use Java. We're in cluster mode as opposed to client mode, where you might use it in a Jupyter notebook. You can specify different images, easy to like swap in and out different images. Here's the location in S3 where a PySpark script is located. There are arguments to that Python script. This is basically saying where to grab the input data and where to send the output data. Oh, sorry. And then you can see here we can specify the resource constraints, the scheduling constraints for both the driver and the executor. And I think this is pretty self-explanatory. Basically, resource requests and limits, and memory overhead for the JVM, server's account so that Spark can access S3, and so on. Yep. So the first challenge with running Spark applications in Kubernetes is that the default Kubernetes scheduler struggles with Spark's two-phase deployment when multiple Spark applications are being submitted. So you can see here when I describe the Spark operator, first the driver pod is spawned, and then the driver pod will request one or more executor pods. But this is a sequential process. The API server has no idea how many executors this Spark application will need to execute the job. So yeah, it may be that multiple Spark drivers are scheduled without ensuring that they can subsequently acquire the necessary executors to operate at like full performance. So it can lead to like saturation of the Spark application. Sorry, it can saturate the cluster with too many drivers competing for limited executor resources. So here's an example. So we have two Spark applications, A and B, and here we have time. So here, Spark application A was submitted first, and the driver requested three executors. The first two were successfully scheduled and run, but during this phase, another driver was scheduled and run, and it requested one executor, and this was probably a smaller data processing job, and it turns out that it's competing for the same resources, and it kind of hijacked the node that this executor was on. So that means that when multiple Spark applications are running, this can lead to unpredictable performance degradation and inefficient utilization of the cluster, because this driver has fewer executors than it needed to run at like full performance. And then finally, default Kubernetes scheduler has, since it considers pods independent of one another, it lacks awareness of entire Spark applications. So an entire Spark application is a logical grouping of driver and executors together. And so, yeah, this means that smaller apps can cut in line, as you could see here. This application B cut in line of this bigger application, and it starved the application A of resources that it needed to get going. So yeah, so to overcome that limitation of the default scheduler, there is a batch scheduler called Unicorn, and this allows for the logical grouping of pods that belong to the same Spark application. And basically, yeah, it will group it will group pods based on tasks, and then add that group to a queue in a first in, first out manner. And then it will have entire groups of pods, which are applications, wait on a queue, which have a finite resource. So if the queue can fit on multiple Spark applications, then both Spark applications will be scheduled consecutively. If a queue runs out of resources, then the second Spark application will be queued and will wait until space is freed up on the queue. So yeah, Unicorn has this it is aware of applications, so it can schedule all pods at the same time. So scheduling all pods at the same time, according to some kind of logical grouping, is called gang scheduling. And the main benefit of this is that it ensures that all components of a Spark application, both driver and all of the executors, are scheduled together. And it follows an all or none approach. So you can see here that through the operator, when Spark submit is run, the driver pod is created. And then placeholder, basically Unicorn creates placeholder pods for both the driver and executors. And you can see those in red. Red means placeholder. And then basically the placeholders will have the same resource requests, resource constraints in terms of memory and CPU and scheduling constraints as the actual application pods. And so if necessary, the cluster will scale up with Carpenter node autoscaler. And then once it scales up, brings up the nodes, and we now have the resources, the compute nodes that we need to schedule all of the Spark application pods together. And so when the nodes are up, the Unicorn will replace the placeholders, driver and executors with the actual pods. So yeah, basically guarantees that Spark applications will have all the necessary resources before starting. So it basically prevents partial deployments for Spark applications which don't have all the necessary executors that they need to get going. And the way you do this is by adding, so the Unicorn, the there's a Unicorn admission controller. Um, and when it sees some labels or annotations, it will mutate the pod spec and inject uh, the scheduler name equals Unicorn. So it will, so that the default Kubernetes schedule will skip this pod and it'll be scheduled by Unicorn instead. And we'll look at that in a demo. So in this little example, you can see this is a Spark application, but now we have labels and annotations which Unicorn will kind of pick up. So here we have the queue. Oh, so we have the name of the application, which will be viewable in Unicorn. We have the name of the queue that this Spark application will be put on, and then we have some annotations. So we have the scheduling policy parameters, which basically says that we're going to set up gang scheduling for the application. And then here we define task groups. So for Spark, we have tasks for both the driver and the executors. And basically this is specifying the minimum resource capacity that must be available before scheduling the pods and starting the job. So you can see that we're going to spin up the placeholder pods, and we're going to have one of them should have this CPU and memory. We should specifically schedule those pods on certain types of machines. We're going to use node selectors and tolerations to target those machines. And then we're going to, when the job starts, so we want a minimum of 4 executors. And you can note for later in the second part of the talk that the driver is on demand and the executors will be on spot. So this is all that is needed to schedule batch workloads. I'm going to give a quick demo of this. So I come out. Bear with me.
I'll just say, but while you're getting that ready, if anybody has questions, remember feel free to just throw them in the chat. We'll pass them on to David.
Oh yeah, if you have questions now while I'm setting up, feel free to ask. Okay, so yeah, I have, as you saw in the presentation, I showed a Spark application spec. I'm going to put this application on a queue called root.sandbox. There is basically limited capacity on this queue. I can quickly show you that I won't go into the nitty-gritty gory details, but in Unicorn you can define various queues, and then from the parent queues you can have child queues, and each queue will have like a maximum amount of memory and CPU, and this will determine how many like Spark applications you can fit on that queue. And if there's one that doesn't quite fit, then it will be queued. It'll have to wait until the other jobs are finished. So here I'm specifying that queue. And as you can see, I'm specifying gang scheduling and the 2 task groups. So I'm going to first make sure I've got rid of all the Spark applications. Okay. I'm going to submit the first one. I'm going to submit the first one. I'm going to submit the 2nd one. I'm going to submit the 3rd one. I'm going to submit the 4th one. I'm going to submit the 5th one. I'm going to submit the 6th one. I'm going to submit the 7th one. I'm going to submit the 8th one. I'm going to submit the 9th one. I'm going to submit the 10th one. I'm going to submit the 11th one. I'm going to submit the 12th one. I'm going to submit the 13th one. I'm going to submit the 14th one. I'm going to submit the 15th one. I'm going to submit the 16th one. I'm going to submit the 17th one. I'm going to submit the 18th one. I'm going to submit the 19th one. I'm going to submit the 20th one. I'm going to submit the 21st one. I'm going to submit the 22nd one. I'm going to submit the 23rd one. I'm going to submit the 24th one. I'm going to submit the 25th one. I'm going to submit the 26th one. I'm going to submit the 27th one. I'm going to submit the 28th one. I'm going to submit the 29th one. I'm going to sub So it's been created, and we can get the status of the applications. You see we have, so this Spark application we picked up by the operator, and it will do the Spark submit for us. And when it submits, a driver pod will be created. And we can see that here in this. Mhm. Okay, so it's been submitted.
Hey, David, can you increase the fonts a little bit? I don't know if that's easy or zoom in a little bit.
Yeah. Oh, how do I do that in the terminal?
I wonder. Oh,
I think,
Command plus also might help too, I think.
how was that?
Yeah, that's better. Yeah, I think it's definitely better on my end for sure.
Okay.
Cool, thanks.
Yeah, so I'm gonna look at the pods. Oh, one sec. Ah, and sorry, I forgot my K9s.
No, no
All
worries.
right.
This is the
Okay.
fun of live demos.
So yeah, you can see here that we have these are the four placeholder pods that Unicorn spun up, and I can describe this pod. You can see the annotations on the pod relating to Unicorn, and go to the events. Instead of the default Kubernetes schedule, we now have Unicorn. Um, and also, if you notice, yeah, also if you notice that at the time of scaling up, at the time of scheduling these placeholders, we didn't have sufficient resources. So Carpenter, I don't know if you know Carpenter, it's a node autoscaler. Basically sees that there are appending pods with certain resource constraints, and that there are no nodes to accommodate those pods. So Carpenter goes ahead and says that the pod should schedule on a specific node. Um, and then it's basically the placeholder is just a container that's running pause. Sorry, and then while we were looking at those events, basically those placeholder pods were replaced by actual Spark application pods. Um, so basically, this demonstrates that the um, the Spark application had all the resources that it needed to get going. It wasn't starved of the resources, um, but we weren't degrading uh, you know resources, and there was no partial deployment. Um, and yeah, this will carry on going. Um, But now I want to show you what happens when we deploy two Spark applications to the same queue. And using Unicorn, we can demonstrate that we won't be starving one application of resources because the two applications will be competing for the same underlying nodes. So let me just get rid of this application.
And I don't want to distract you, but there was a question from Omer. It says, can you please explain how the operator handles spot interruption from the executors?
Yeah, so the Spark operator, or more specifically, the driver will have mechanisms to handle executor failure when the executor is lost. The driver automatically requests a new executor to replace the lost executor. And actually, that's going to be the second part of my talk. When that happens, if you don't have any mechanism to um, you know, handle gracefully that node failure, then you can lose important shuffle data that was generated at that like particular moment when the executor was lost, and that can increase your runtime and like make the job run for a lot longer. So yeah, that's going to be my second part of the talk where we show how to handle spot interruptions.
All right, thanks.
Yeah, so now I'm going to submit two. So this pod's are gone. I'm going to submit two applications. And they're basically doing the same thing. But if you remember, the queue, the Unicorn queue had a limited capacity, and it wouldn't be able to handle two applications at the same time. They'll have to wait for the Spark application or the operator to submit the application before the driver shows up. Take some time. Yeah, this is the time to ask you questions. Okay, submitted. Okay, so we should see. Yeah, so we already see the driver and placeholder pods. So they'll already be on the queue. Now I'm gonna submit a second one. And it's exactly the same, except for a few, I think I may have modified the resource requests and limits and changed the application name. But yeah, I'm gonna submit that too. And then we can go back to KNS. And so you see this is already running actually. And we should see the second one come up, but it won't be able to run immediately. While that's being submitted, there is a Unicorn UI where you can check out. Yeah, so you can see we have the first application, taxi trip app 1, and we have app 2. And if we look at app2 and describe it, look at the events, it should say that it cannot be run. There you go. Unicorn is giving a message that this executor, which is part of that gang or that task group, is queued and waiting for allocation because there's not enough space on the queue. So it ensures fairness, like scheduling fairness to entire application, not just pods. And you can see this. Can you see my new Unicorn UI?
Yeah.
Yep. Yeah. So you can see here. You can view specific applications on particular queues, and you can see the two applications that I submitted. First one's running because it fits on the queue, but the second one is accepted, but it's not allowed to run yet because it has to wait for the second one to finish. So yeah, just to reiterate, with the default Kubernetes scheduler, priority and fairness is only given at the pod level. So it could be the case when you saturate the cluster with multiple drivers that smaller applications could cut in line and steal needed resources from bigger data processing jobs. I hope that makes sense. Okay, so I don't think we need to wait for these to finish, but yeah, basically when these finish, these placeholders will be replaced, and this will run. But if the queue had enough space to accommodate both of these applications, then both would run at the same time. So I'm gonna go to the next section, if I can find my tool.
There was one more question,
yeah.
but if it makes sense, like if you're going to answer this later, then
Oh no, please, please ask the questions.
Sure. Okay, this is from Caslin.
Yep.
It says, I was taking notes and might have missed it, but how does your application-aware scheduling problem relate to Kubernetes resource requests, limits, and taints tolerations? And then, sorry, and then the follow-up was, it seems like those tools must be insufficient to solve the problem, but Unicorn addresses it well. Have I got that right?
So if I understood the question correctly, the person is asking how does Unicorn solve the problem of resource constraints and scheduling? I don't quite understand the question.
Let's see. Okay, let's see.
But basically, basically use the Unicorn task group spec to specify the minimum resources which should be made available for the actual pods, and they must match the pod spec of the actual driver and executor. So take this as an example. You have node select and tolerations here, and the driver should be on a machine that can accommodate 6 gig and 1 CPU. And this matches exactly what we have for the driver in the actual main spec of the Spark application. So we have 1 CPU. That's for the executor. But same idea. We have min members, the minimum number of pods that we would like to schedule for the main application. So this is that's saying that we will schedule 4 placeholders, and they're going to ensure the minimum underlying compute in terms of EC2 nodes, and it's going to bring up EC2 nodes which are tainted with these labels, so they're the right type of machines. Basically, the resource constraints is 6 gigabytes matches up with this. So it's memory plus memory overhead. This corresponds to JVM. So it's just ensuring the minimum compute at an application level while respecting resource and scheduling constraints. If that makes sense.
Yeah, great. Thank you.
Was there a second question?
Oh, well, there was, okay, maybe in you maybe answered this, but so you need a higher level of abstraction than the pod, something that takes into account resources like deployment and maybe volumes.
Uh, so, that's a good question. The We could probably get onto volumes in the next section.
Okay.
Yep. Yeah. So let's move on. So yeah, next section is there was a question on how do we handle how do we gracefully handle spot interruptions. So yeah, this section. Oh, sorry about that. Yeah, so like I said before, though those Spark executors are resilient to spot interruptions, um, because the driver will detect that an executor was lost and request additional executors to replace that. The shuffle files, and I'll explain what shuffle files mean in a second. Uh, Basically, yeah, important data that is read into disk is going to be lost when the executor gets killed. And that means that that data will need to be recomputed, which will increase the overall runtime of the job. And Spark released two features to address this issue. One was oh yeah, one is like called node decommissioning, whereby executors upon receiving that termination signal in that 2-minute grace period will copy over any important data to neighboring executors. And if an executor doesn't exist, it can fall back to S3. But there's another approach too, where we can use persistent volumes attached to each executor to store important data. And when an executor gets killed, the persistent volume claim can reuse the data on the PVC can be reused by the new executor that comes up. So yeah, this is just going to improve the overall resiliency of the application and increase or decrease runtime. So yeah, basically, you can in a Spark application running on Kubernetes, you can put the driver on demand instances, and they must go on demand because they're the drivers, right? They hold the critical metadata and the execution state of the entire job. It's the thing that's orchestrating everything. But the executors, however, can go on spot instances because they're doing a bunch of stateless computation, don't store any critical metadata. And although spot instances do offer like steep discounts, they come with a caveat. They can be reclaimed at any moment. And so, like I said before, while Spark can be resilient to interruption by requesting additional drivers, it can result in lost data and having to waste time recomputing data that we've already operated on. So it's adding to the runtime of the overall job. So yeah, the loss forces recomputation of files, and basically you have to either go back to the last cached stage, or worse, you had to go back to the original data source. And so just to appreciate why this process is so time consuming, just going to go through a brief high level overview of what's happening under the hood. So Spark, Spark is used for data processing. I don't know if you've heard of pandas, but it uses like data frames, and you can perform various operations on the data. And there's a specific type of operation which causes a reorganization of the data across nodes in the cluster, and it's this operation which is expensive. So there is one such operation called group by key. This basically data from all the partitions on all the executors. So here we have 3 executors, and they have the data is organized according to partitions, and group by key. Sorry. Basically, each one is holding a set of key value pairs, where the key is a word and the value is basically a count. And basically, this data is redistributed across the cluster so that all counts for a given word end up on the same executor, ready for aggregation. So you can see that the word hello ended up on this executor, and we have two ones. So it's basically sorting and merging values ready for aggregation. But it's expensive because all of these all of this data has to be written before it's transferred over the network from source to target. It has to be written to disk. Once it's on the source executor, it has to be read from that disk. And then you can see here the values have to be sorted and merged. And this is very CPU and memory intensive. So it's shuffle. This group by key operation, which causes a shuffle, is inherently expensive. So if we lose an executor due to spot termination, we lose all the shuffle data it held, which means we'll have to potentially repeat all of these steps or only specific steps. And we may have to go back one stage or to the original data source. So it's basically adding a lot of time onto our entire job, and it's going to slow us down. And basically, this is why developing a strategy to persist the shuffle data, like for instance, this data to disk, allows us to quickly recover from the event that we lose an executor. So yeah, it's a balancing act between saving money and maintaining job performance and reliability. So this is basically the way it works. And if you're curious to learn more, there's a AWS blog on how it works. But using a persistent volume claim, which is tied to an EBS volume, allows us to decouple the data and the processing, because we can use it to spill the shuffle data into kind of like local storage. So you can see here we had a Kubernetes SIG term, which comes from the spot termination. I'm going to wait for it to come back. Yeah. And it kills the executor. And within and we don't have to do much in that 2-minute grace period, because the data is stored locally on the EBS. We don't have to move it around. And then basically the persistent volume claim, which is tied to the EBS, is not tied to the lifetime of the executor, because the Spark driver owns that persistent volume claim. So so that when a new executor comes up to replace the old executor, the persistent volume claim can be reattached or can be attached to the new executor. And so that means we don't have to recompute the shuffle files. And the new executor can pick up where the old executor left off before it got killed. Yeah, this allows us to save time required to request a new volume for an executor, and the files can be reused without moving files around because they stay on the EBS volume. And to enable this, you just have to add specific configurations to the Spark conf in the application. I think there was a question about specifying EBS volumes in the Unicorn config. So that is done actually dynamically by the driver. So the driver is the one that's requesting persistent volume claims tied to EBS volumes through, and it assumes that you have the EBS CSI driver installed in your cluster to dynamically provision and manage the lifecycle of EBS volumes. And that's what we're doing here. We're giving the name of the claim, the storage class, GP3, the size, the mount path inside the container for the driver and executor. And we're going to be writing to read-only false. And there will be a separate EBS volume per executor. And then these settings are so that the driver owns the PVC, meaning the PVC is not the PVC is not tied to the lifetime of the executor. So when the executor dies, the PVC remains. And here this means that the new executor that comes up can be reused. So I'm gonna give a quick demo. Basically, this demo is just gonna show that we can still run a Spark application, I guess, in the expected time, even after manually killing one of the spot nodes. So again, I'm gonna delete all the apps, and this is the time to ask your questions. So I'm gonna submit this app, and again, same one I ran before, and also notice those labels in the Spark config. So you can dynamically mount PVCs per executor, given a storage class and size. It's basically saying that the driver pod becomes the owner instead of the executors. And then this label is saying that instead of creating a new PVC, we can kind of reuse the old one. So I'm gonna apply that. Okay. I'm gonna look at the nodes. I'm gonna want to kill one of them. Well, I can probably see that in here actually. Okay, so sorry. Okay, so the job was submitted. We have our pods. They haven't been scheduled on a node yet.
But just so you know, someone had put a comment about asking, saying they're pretty new to this and asking if this is all open source. And I pointed them to the both the Apache websites, letting them know that
Yeah,
Spark and Unicorn are both part of the Apache Software Foundation.
yeah. These are all open source. They're installed. Both Unicorn and the Spark operator are installed as Helm charts. Basically, when I spin up the EKS cluster with Terraform during the bootstrap stage, I install these things as charts. But basically, I would recommend basically starting on this journey through going to actually it's a similar acronym, data on Kubernetes versus data on EKS. And here there's a set of blueprints to help you get started with deploying data applications on Kubernetes. So you can see, oh, sorry, I forget where it is. Blueprints. Oh yeah, here. So this is a set of blueprints, and you can see um, data analytics on EKS, Spark operator with Unicorn. So this goes into a lot more detail than I'm going into. And they have like a whole guide on deploying the solution, Carpenter, Unicorn. Uh, I showed using EBS volumes to store data, but they also show examples of using local instance storage for shuffle data. So yeah, I would recommend going to data on EKS and checking out their blueprints. They have a bunch of they have a GitLab repo too that you can check out. So yeah, great resource. Uh, okay, so it looks like they put them all on the same node, but it doesn't matter. There's an EBS volume per executor, and we'll wait for it to get started, and then we'll kill it. That is another thing to mention. You know, this application had 4 executors. Maybe you don't want them to be all on the same node. So you can add pod affinities, topology spread constraints to force a spread of the pods across different nodes. But I didn't do that here. And I think Carpenter just picks the node, tries to bin pack as many pods on the same node. So you can see, oh, I forgot how to see the logs. Oh yeah. So you can see it's going along. It's performing tasks across the executors, 1, 2, 3, 4, 5, 1, 2, 3, 4. And I'm gonna kill one of, well, I'll be killing them all. So let's take this IP.
Just an FYI, David, we're running up to the hour shortly.
All right, I'm nearly finished.
Cool.
I'm gonna kill the node, and then we're done.
That sounds very dramatic.
Where are you? There. So I'm simulating a spot termination. Okay. So it's terminating, and we can look at here, decommissioning not enabled, trying to create persistent volume. and it will say it doesn't need to create one because it's going to reuse one. Right, it's requested we deleted pods 1, 2, 3, 4, now it's going to spin up 5, 6, 7, 8, and it will reuse an existing PVC. Oh, it said reusable. Yeah, it's still pending. But yeah, that is the end of the talk. When these pods come up, you can show that they reuse the existing PVC. But yeah, I'm guess I'm done. But yeah, main takeaway is yeah, so we can use a batch scheduler so that a batch schedule which is application aware, so we can schedule all pods together to ensure that the application has the resources it needs to get going, and also that we can be resilient to spot termination by reusing data that's stored on PVCs. Thank you.
Awesome. Thanks, David. Um, maybe there was a couple more questions. Maybe we can throw them in the Slack chat um, for DOK, and then I'll ping you, David, if you can answer. That'd be awesome. Um,
Sure.
um, but yeah, thank you so much. Yeah, and thanks everybody for watching. I think that was
Thank you.
very informative. So I think you helped a lot of people out there. Um, we'll try and get through our DOK quiz real quick. I know we're past the hour a little bit, but we'll if anybody who's still here and wants to participate, let's let's go for it. Let's do that. And Digest will be queuing that up in just a second. Okay, so bust out your phones and scan that QR code. You can take part in our quiz. Just ask questions over some things that David talked about and maybe some things that I talked about. We'll see. Yeah, it's just for fun. So if you win, you can get a DOK shirt. There's a little delay, so we'll wait for people to register. David, you can participate too, although you might have an unfair advantage.
That was going to be my next question.
All right, we've got some participants here. All right, one of 5 questions. Let's do it. And the faster you answer, the more points you get. So, what is one of the main benefits of running Spark on Kubernetes? All right, we've got 4 answers in. Okay, everybody's voted. Let's see who's in the lead. All right. We don't. This is anonymized, so we don't know who's who. But St. Elmo, fastest and correct. And by the way, at the end of this, since I don't know who it is, message me on Slack, however, um, LinkedIn, or whatever, and let me know, and then we'll get the information to send you the shirt. All right, which component is described as providing application-aware scheduling for Spark jobs on Kubernetes? We've got the Spark operator, Carpenter, Unicorn, Argo workflows. Uh-oh. Wait a second. Okay. All right. St. Elmo still in the lead, I think. Oh, wait.
Oh,
We have a new
who
new
did you?
leader. Oh wait, there's some reshuffling. Okay, you're right. Stadium Elbow still in the lead here. Question number 3. What type of scheduling does Unicorn provide for Spark applications? Round robin, priority based, all or none gang scheduling, or random scheduling? Ooh, all right. Everybody got it right. Oh, we even got a new player. I think went from 5 to 6 players. Okay. Ooh, it's so close. All right. It's going to come down to this last question. Whoever gets this fastest, I think. Okay. Oh, no, sorry. There's 2 more questions. Okay. What are the 2 strategies mentioned for running fault tolerant and cost optimized Spark clusters in EKS? I think this is one of our most challenging quizzes. Everybody needed to pay attention. Oh wow, this is actually one of the closest games I've seen. All right. Okay. Question 5. This is the last one, I promise. This is not technical. When will DOK talk announcements occur? So you had to pay attention to me, and if you were here early, you benefit from that. So August 26th, August 30th, September 10th, or September 19th. Ooh, okay. The one person who really heard me. Tells you, it benefits you to listen to me at the beginning, what I have to say. The community announcements. Okay. All right. This was pretty close. So I think we'll find out who. I think maybe Saint. Oh, wait. Did the Hustler win? I can't tell. Diogenes. Is that is that the winner?
Yes, that's the winner.
Oh, wow. Came from behind. The Hustler. Okay. The Hustler. If that's you, reach out to me on Slack or LinkedIn, wherever you can find me. I'm Paul Au on LinkedIn. AU, it's my last name. Or on Slack. Let me know and we'll get you a shirt. But yeah, once again, David, thank you so much. Really appreciate you taking the time. This was a really informative talk. So really appreciate you taking the time to do that. And then also thank you to everybody who came to the talk and asked questions. And like I said, I'll post the question in Slack, the last couple of questions, and maybe David will be so kind as to answer them for us. All right, cool. Well, everybody, thank you for coming, and we'll see you at the next one.
Great, thank you.
All right, see you
Bye.
later. Bye bye.